So A goes to B reversibly, and then B goes to C. And I haven't told you anything about equilibrium, okay? Then what do we get for the rate of consumption of A? What's the rate law? All of these are elementary, so this is something that we did way back in the beginning of class.
K1CA minus K negative 1CB.
And now what's the rate of B? We could write it as production or consumption, it doesn't matter. I'll write it as production.
K1CA minus K2CB.
You left one out.
Oh, yeah. Minus K negative 1CB. Minus K2CB.
And now what's the rate of C?
K2CB.
Okay, so to solve for the formation rate of C, I have to know the concentration of B, right? And so what we'll then do is we can say, let's assume that the concentration of B is low and that it's not changing very much over the course of the reaction. So remember the last class we had A goes to B goes to C, and one of the curves I put up looked like this. And this was for the case when K2 over K1 was equal to 10, and then you had a curve that looked like this. This was K2 over K1, 1, and then this one was. Remember that? So it's not always an appropriate assumption to say that the concentration of B is always low and never changing. But sometimes it is. And so then we can come back and we can write out this on B, which means that we can set this to 0. And I can rearrange and solve for B, the concentration of B. One sec. And so then I can say that if this value is much larger than this one, K minus 1 is much larger than K2, then what does that equation become? What's that equation? The K2 drops out. Okay, so you get CB. What's the ratio of these two rate constants?
K.
Big K equilibrium times the concentration of A. This is not the same as saying equilibrated, though. This is saying that a reaction is quasi-equilibrated. Which means, though, that I could write the rate of C is simply equal to K2 times big K1 times the concentration of A. I'm substituting in for CB right there. So that's what you do in a quasi-equilibrated reaction. You make an assumption based on the pseudo-steady state, and then we have to make an additional assumption, though. This is only true if the reverse rate constant is much faster than the forward rate constant that's depleting B. In other words, if I have A and B goes to C, this will go back and forth maybe 1,000,000 times before this happens once. And because it's going back and forth so rapidly, it's basically equilibrated. It's not, though, because it happened one more time in the forward direction than it did in the reverse. It had to, because otherwise there's no way to do B to C. So that's how you deal with, so this is a good review, because you're probably going to have something, this was the first homework, right, was series of rate equations and deriving the rate equation based on things like pseudo-steady state approximation. And that's what leads to quasi-equilibrated relationships that you can use. But this relationship is always true when you're at equilibrium. I haven't made any assumptions except that I'm at equilibrium. And it's never true any of the rest of the time, right? And this relationship also means that the rate of reaction 1, the net rate, is equal to what?
0.
0. But again, that's only true at equilibrium. Yeah.
I think that what Robert was saying was that in order to get from concentration B over concentration A to equal K1 or K -1, you have to assume the rate of A is 0, which is true at equilibrium.
Sure,
It's not
but you don't have to
steady state,
assume that.
It is, you can apply steady state because it is at equilibrium.
Right. You don't. I mean, I guess it's more semantic. I wouldn't say that that's an assumption. I would just say the definition of equilibrium states that the rates are 0. It's not an assumed thing about equilibrium. It's literally the definition, is that the net rate is 0. So that allows me to write it this way. But yeah, I mean, you can write it. I mean, you can see where it comes from right there. If I set that equal to 0 and rearrange this equation, I'll get these ratios. Yeah.
And just to check, PSSA, we can never assume prior, like going into the problem. It's something we like figure out or we're told explicitly, right?
I wouldn't go that far.
Okay.
But if you're going to use it, you need to state that you're using it. You know, you need to say, I'm applying the PSSA to this species B.
Gotcha.
And you might even mention that, like, once you've solved the problem, you could go back and check for that.
Okay, gotcha.
But notice that PSSA didn't do this part. This is a second assumption that will lead to whether or not the first reaction is quasi-equilibrated. That's an entirely separate assumption. There's two assumptions at play. One just helps me write out the rate of C, which is just to say that at steady state, or in other words, I can treat this as a pseudo-steady state problem, assuming that B is not changing all that much. And that allows me to get rid of B, the concentration of B, when I'm writing out the rate of C formation. Yeah. Yes?
For the equilibrium equation you boxed in over there,
Yeah.
if we have coefficients like small a, small b, they'd be exponents in that, right?
Yes. Yeah. And so it's just products over reactants, right? So if I have 2B, that's the same thing as saying, B plus B. And so this is always just going to be the product. Now I'm going to lose people, of products over the product of reactants. And that's true whether or not things are, I don't want you guys to get confused, because when we have elementary rate laws, right, it's very similar. You have the rate, and then it's just the product of the reactants. So in this case, it's K1 times concentration of A. If it were 2A, it'd be 2A, right? If it were B plus 2A. So it's very similar to an elementary rate law, but the equilibrium definition doesn't require this to be an elementary step. There's no such requirement. It's just going to be whatever this is. So in this case, it would be B squared over A squared times B, which is a bit silly to write it that way, I guess. Any other questions? Yeah.
Can you do the one when it's leaking out the reactor? B is?
Where B is leaking out the reactor? We had a problem where B was leaking out of the
Isn't that
reactor.
membrane or something?
Yeah, that's what you're avoiding.
On this homework?
Not the homework, it was last homework.
Oh. I know what you're talking about.
Yeah, it was like B was leaving out some membrane as it was forming.
We're not going to have any membrane problems. I didn't know you did a membrane example. We didn't assign a membrane example on the homework,
Just did
did we?
one problem, I think.
Yeah.
It was the all-in-one problem, I think.
Oh, he just kind of took it too far. Wait, I don't want to do that one because we're not going to worry about membranes.
So it'll always be like just the reaction, nothing like, I mean, like obviously like PFRs and stuff like that, but I mean like, we don't have to worry about any kind of outside, like, oh, slowly this is trickling out, or, reactants are slowly decreasing as they're getting inserted or something like that. You don't have to worry about that?
No. We don't have any membrane problems. I think the only problem that is maybe similar to that, but it wouldn't be on the test, is the drinking problem on this homework. where there's a little caveat where if you're drinking it slowly over the course of an hour instead of all at once, you can treat that as a series of 2 reactions. So A goes to B as you drinking, B goes to C as your body processing the alcohol. But no, you're not going to have anything like that on the exam. Now, I think what he probably did was like, that was probably like a part A through I problem, and I think like at the very end it was like, now what if it was in a membrane? And I probably just should have told them, don't do that membrane.
Yeah, that's a weird problem.
Yeah. There's a couple like that in the book where they just, in fact, one of the homeworks problems this time, I stop it at like G, and I think H and I are, now what if it was in a membrane? Any other questions? Okay, let's start talking about heat transport. We'll get a little bit of a head start on the second part of the class. Again, I think this part is substantially more difficult, so the second test will cover this section, and that's part of why the time between the first test there's a lot of material, the second test there's going to be less material. So I think it's harder material.
How many exams total on that?
2 exams and a final, but I'd like the final to be the last day of class, but that'll just depend on,
Circumstance.
yeah, that we don't fall behind, which I doubt we will, because I feel like we're way ahead. And we're going to do some other things. In the third unit, after the second exam, we're going to talk more about catalysis as the third unit, and so you'll have a problem on the final about catalysis. And within that, we'll talk as well. So we skipped a chapter, which was the collection and analysis of rate data. I wanted time to, I'm going to give you guys rate data from my lab, and that way you'll be holding real